During the early formation of our solar system, four small rocky worlds assembled in the region where the radiation of an infant sun was strong enough to push away light gases and destroy all ice. But at greater distances, hydrogen, helium, and ices like water and methane were plentiful, and in this region, four giants were born: Jupiter, Saturn, Uranus, and Neptune. Through their immense gravity, these gas giants vacuumed up all available gas in the early history of the solar system. Humanity's curiosity eventually extended to these distant worlds. We had explored the inner solar system, Mercury, Venus, Mars, but the great outer planets beckoned to the scientific community. An expedition to the giants, however, would require crossing a protoplanetary graveyard, a ring of asteroid debris 160 million kilometers beyond Earth's orbit, the belt between Mars and Jupiter. With only basic telescopic observations of some objects in that region, a critical question loomed. Could a spacecraft survive the journey? Crossing the asteroid belt. In 1972, NASA's Pioneer 10 became the first spacecraft to enter the asteroid belt. Popular imagination paints it as a rubble-strewn gauntlet of house-sized objects crashing together in slow motion, but the reality is quite different. Scientists estimated only a 1 in 1,000 chance that the spacecraft would suffer a serious collision. There is a great deal of rock out there, but it is spread over an enormous volume of space, and collisions, while they do occur, are far less frequent than people imagine. 7 months after entering the belt, Pioneer emerged triumphant. Having a spacecraft extend its reach into the outer solar system was another important stepping stone in our exploration of the universe. By year's end, the probe completed a flyby of Jupiter, and Pioneer 10 remained humanity's most distant spacecraft until 1998. A great deal of what is most interesting about our solar system had been beyond our reach, until Pioneer 10 showed the way. The Voyager Grand Tour. In the 1960s, engineers at NASA's Jet Propulsion Laboratory noticed an imminent alignment of the outer planets. A spacecraft would be able to harness the gravity of each planet and swing from one to the next using minimal fuel, a concept known as the gravity slingshot. It was recognized that one could accomplish a grand tour, rendezvousing with more than one planet in sequence. If NASA missed the opportunity, however, the alignment would not recur for nearly 2 centuries. The Voyager program was an epoch-making moment in the annals of spaceflight. Twin probes, Voyager 1 and Voyager 2, were crafted together to provide unprecedented access to the outer reaches of the solar system. For the first time, scientists would have images of those distant bodies in extraordinary detail. But more than that, the probes were designed with longevity in mind, built to endure and to keep transmitting for as long as possible. By today's standards, the Voyager spacecraft were quite basic vehicles. They carried old television cameras, not unlike those used in a television studio at the time, and 8-track tape recording systems. Nevertheless, the equipment proved capable of revealing secrets that had long been hidden from us. Each Voyager probe also carried something of humanity itself. The legendary scientist and communicator Carl Sagan decided to send a cultural object along with the scientific payload, the now famous Golden Records. As Sagan himself said, "I send greetings on behalf of the people of our planet into the universe, seeking only peace and friendship. To teach, if we are called upon to be taught, if we are fortunate. Nominally a message for any alien species that might find the probes, the records were equally a message to ourselves. It was a declaration that we have something special on our planet worth sending out into space. If extraterrestrial life could decipher the instructions to play it, the record would reveal 115 images, 90 minutes of music, and greetings in 55 different languages. Voyager 2 was launched first on August 20th, 1977. In less than 2 years, each probe arrived at the first stop on their grand voyage. Jupiter, king of the planets. The largest of all the gas giants, Jupiter contains 2.5 times the mass of all the solar system's other planets combined. It formed from countless small globules of matter colliding in the very early days of the solar system. The infant world hungrily swallowed nearby asteroids and comets, and as it cooled, it accumulated enormous quantities of gas, resulting in a solid core surrounded by a vast atmospheric envelope. Jupiter is truly the dominant force in our solar system, second only to the Sun. Pioneer 10 had captured our first close-up images of Jupiter, but the Voyagers exposed far more of the planet's secrets. When Voyager drew close, it saw a very complex place, weather patterns that bore surprising resemblance to those on Earth. Among the key targets was Jupiter's Great Red Spot, a storm system analogous to a tropical cyclone, but enormous. First observed nearly 400 years ago, it has simply persisted, a fact that remains fascinating and not completely understood. In the 19th century, the Great Red Spot stretched 3 Earth diameters across. By the time the Voyagers visited, it had decreased to 2. The scale of Jupiter is a striking reminder of how small we are. When you look at its features and realize the entire Earth can fit within them with space to spare, it is truly the land of giants. Voyager 1 also revealed a completely new feature: rings. So faint that no one had spotted them from Earth, these rings were likely formed by Jupiter's moons shedding dust into orbit. Future discoveries would reveal rings around every gas giant in the solar system. Saturn went from being the solitary jewel of the ring planets to just one member of a whole family. The Voyagers also investigated Jupiter's natural satellites. The moons of Jupiter are pivotal in human history because Galileo's discovery of the 4 large moons in 1610 helped disprove the geocentric model of the universe. It demonstrated that Earth, the other planets, and their satellites all move in orbit around the Sun. The innermost of the Galilean moons, Io, is a hellish world home to as many as 400 volcanoes, spewing sulfur dioxide in prodigious quantities. The Voyagers captured a surface covered in lava and sulfur. The cause lies in Io's close elliptical orbit around such a massive body. Jupiter's uneven gravitational pull drives rocky tides, and Io's surface bulges in and out by as much as 100 meters on each cycle. The frictional forces keep its interior warm and its subsurface rock liquid, making it the most volcanically active body in the solar system. But it is the smallest Galilean moon, Europa, that holds the most scientific interest. Scientists believe Europa harbors a subsurface ocean containing more water than exists on all of Earth. We can see the effects of convective currents flowing to the surface and breaking up the ice. It is a circulating ocean, and where there is water, there is the opportunity for life. We are now speaking of the potential of Europa as a living world, with liquid water, a strong energy source, and organic chemistry. On Earth, those same ingredients produced life in less than 1 billion years. Closer images of Jupiter and its moons would have to wait until the end of the 20th century, when the Galileo spacecraft was deployed from the Space Shuttle Atlantis in 1989. Its journey to Jupiter would span 6 years. En route, Galileo witnessed an extraordinary event. In 1994, the spacecraft watched as the comet Shoemaker-Levy 9 was torn apart by Jupiter's gravity, its fragments subsequently crashing into the atmosphere and releasing colossal amounts of energy. Each impact scar thousands of kilometers wide. The collision demonstrated how Jupiter's gravitational presence shapes the entire solar system. Because of its gravity, Jupiter pulls comets and asteroids into itself, and it is very likely that this has shielded Earth from many impact events throughout our history. As part of the Galileo mission, a small atmospheric probe accompanied the main spacecraft, designed for a brief but crucial encounter with Jupiter's clouds. In December 1995, the probe plunged beneath the cloud tops, hurtling to a final measured depth of 180 kilometers. It discovered lightning, measured temperatures and pressures, and confirmed long-held theories about Jupiter's dynamic atmosphere. In 2003, a dying Galileo was deliberately steered into Jupiter's atmosphere. The spacecraft had not been sterilized prior to launch, and this act of deliberate destruction ensured that no surviving microbes could contaminate Jupiter's potentially life-bearing moons. In 2016, the solar-powered Juno spacecraft arrived and settled into a polar orbit. The purpose of the Juno mission was not merely to image Jupiter's clouds once more, but to understand what lies inside the planet and how gas giants actually form. On each of its highly elliptical orbits, Juno passed within a distance equivalent to skimming around a basketball from just 1 centimeter away, at tens of thousands of kilometers per hour. Juno revealed a wibbly-wobbly core in Jupiter's interior, generating a magnetic field some 20,000 times greater than Earth's. The spacecraft was built with significant shielding to protect its electronics from the intense radiation during these close approaches. Deep inside Jupiter, the hydrogen ceases to behave as a gas, becomes compressed into liquid, and takes on metallic properties, and Juno has helped us understand that structure in remarkable detail. Saturn, the ringed world. As we entered the 1980s, both Voyagers approached their next target, Saturn, the second largest planet, named after the Roman god of agriculture. Observed since antiquity, its rings were a source of bewilderment to the first telescopic observers. When Galileo turned his telescope toward Saturn in the early 17th century, he was genuinely confused. The best description he could offer was that the planet seemed to have ears. In 1659, Dutch astronomer Christian Huygens employed a more powerful telescope of his own design and deduced that those ears were actually a system of rings. Each Voyager spacecraft arrived at Saturn apart in time, but together they revealed a great deal. They discovered rings that had not been detected from Earth, a system 200,000 kilometers across, but only about 10 meters thick on average. The probes resolved those rings into their component parts. Tiny dust grains, up to boulders as large as mountains, racing around the planet at 88,000 kilometers per hour. A strange magnetic field suspended dust particles above and below the ring plane. With the Voyager's new data, the puzzling origins of the rings came a little clearer. Whether they had formed with the planet itself or materialized later from a smaller body destroyed by Saturn's immense gravity remained uncertain. It was possible that a relatively recent event, an ice moon drawn too close to the planet, had shattered into the rings we observe today. Christian Huygens had also discovered Saturn's largest moon, Titan, in 1655. In 1997, NASA, ESA, and the Italian Space Agency launched a joint exploratory mission named after both Huygens and the Italian-French astronomer Giovanni Cassini. In many ways, the Cassini-Huygens mission grew directly out of what the Voyagers had glimpsed near Saturn, a world that was utterly tantalizing but incompletely understood. The mission consisted of two separate spacecraft, the Cassini Orbiter, a NASA project, and the Huygens probe, which came from Europe. These two teams from different sides of the Atlantic achieved far more together than either project could have done alone. Cassini-Huygens arrived at Saturn in 2004, the first mission to orbit the planet. Cassini provided unprecedented detail of Saturn's rings by flying through them, requiring mission control to navigate the craft precisely through the debris on every pass. The spacecraft detected evidence of water falling out of the rings at roughly 40 tons per second. The rings themselves were literally raining onto the planet's surface. Cassini also observed a hurricane-like structure on Saturn, the Great White Spot, and watched a hexagonal atmospheric feature at Saturn's North Pole shift in color from blue to gold. This hexagon is the result of a massive polar hurricane roughly 50 times the size of Earth. Another reminder that weather systems on these gas giants can dwarf anything we experience at home. On July 19, 2013, Cassini imaged Saturn and its entire ring system during an eclipse of the Sun. One of the most spectacular images it returned was taken from the far side of the planet, looking back toward Saturn with the Sun lighting it from behind. Spanning over 650,000 kilometers, the photograph detailed Saturn's second outermost ring, composed of fine icy particles. It also featured a pinprick of light, Earth, 1.4 billion kilometers away. NASA knew Earth would be in the shot and invited people around the world on that day and at that moment to go outside and look toward the skies, knowing that their own photons would be captured in the image. During its mission, Cassini snapped images of many of Saturn's moons, but one held the spacecraft's attention above all others: Enceladus, Saturn's sixth largest moon. Its distinctive southern stripes sit atop a saltwater ocean, buried kilometers below its icy surface. Close inspection by Cassini revealed cracks in that ice and water geysers spraying outward from the subsurface ocean. These eruptions fling material into space, which means that one does not even need to land on Enceladus to access this ocean. Cassini was flown directly through those geysers and was able to taste those waters, finding them warmer than expected and full of both simple and complex organic chemistry. Thermal vents at the floor of such an ocean could potentially support life. If forced to bet on the best candidate for life in our solar system, many scientists would pick Enceladus. If a small, cold moon orbiting Saturn harbors the conditions for life, life may be far more common across the universe than we once imagined. Decades before Cassini, Voyager 1's brief encounter with Titan had whetted astronomers' appetites. Titan's secrets were buried beneath a thick, hazy atmosphere, opaque in much the same way smog clouds a city, because of a rich hydrocarbon composition dominated by ethane and methane. After deploying from Cassini on December 25, 2004, the Huygens probe descended through Titan's atmosphere for 2.5 hours. becoming the first craft ever to land on a body in the outer solar system. It revealed a world with ice mountains, sand dunes, and river-like features. They were not cut by liquid water, but by organic molecules of ethane and methane raining from the clouds. Those molecules flow across a water-ice surface and collect in vast lakes. It was almost primordial. A snapshot, many thought, of what early Earth might have looked like some 3 billion years ago, when life was just beginning to take hold. If life formed on Earth under similar conditions, perhaps it is forming, or has already formed, on Titan. After 20 years in space and 294 orbits of Saturn, Cassini was running low on fuel. The mission embarked on a final, daring first, a journey between Saturn and its rings. Diving through that narrow gap 22 times, Cassini sought to determine the ring's age. In 2019, astronomers revealed the answer, somewhere between 10 and 100 million years old, a fraction of the age of the 4.5 billion-year-old planet they encircle. Cassini's final act was to plunge into Saturn's atmosphere, transmitting crucial data right until the signal was lost. It was a fitting scientific end. Uranus and Neptune, the ice giants. Voyager 1's mission to Titan had set it on a lonely outward trajectory, leaving Voyager 2 to carry the responsibility of visiting the 2 remaining outer planets. Sir William Herschel first observed Uranus on March 13, 1781, the first planet discovered in the modern age, previously unknown to the ancients. Just over 2 centuries later, Voyager 2 approached within 82,000 kilometers of Uranus's cloud tops. Uranus is an oddity. The spacecraft revealed high-speed jet streams racing through its polar regions and equatorial zones, and showed something of the planet's unusual atmosphere in greater detail than Earth-based telescopes ever had. Uranus lies on its side, with an axial tilt approaching 98 degrees. The result, scientists believe, of a collision with an Earth-sized object long ago. Its atmosphere reaches the lowest temperatures of any planet in the solar system, plunging as low as minus 224 degrees Celsius. The ice giants receive only a tiny fraction of the sun's light, between 100th and 1,000th of what Earth receives. Uranus's distinctive blue-green coloring comes from methane in its atmosphere, which exists in higher concentrations than in the larger gas giants. Like all the outer planets, Uranus has its own ring system, the brightest of which had been discovered a decade before Voyager arrived via the Kuiper Airborne Observatory. Voyager 2 also provided close-up images of the moon Miranda, one of the strangest bodies yet observed in the solar system. It appears as if Miranda was smashed apart and then reassembled very poorly, one half covered in deep parallel furrows and the other resembling a typical cratered moon. The 2 hemispheres pressed together in a single incongruous body. Miranda features cliffs over 20 kilometers high, and its gravity is so low that someone standing at the top of such a cliff, then jumping, would take about 20 minutes to reach the bottom. In August 1989, Voyager 2 approached Neptune, a planet discovered not by telescope, but by mathematics. Neptune's existence was inferred from its gravitational influence on Uranus's orbit before it was ever directly observed. Communicating with Voyager 2 at such a distance required a significant technical achievement. As a probe travels farther from Earth, its radio signal grows progressively weaker, requiring larger and larger antennas to receive it. In 1986, NASA expanded its deep space network, 3 communication complexes positioned around the world to maintain full coverage of the sky. Each station has a 120-degree field of view and the network was built with stations in California's Mojave Desert, near Madrid in Spain, and near Canberra in Australia. Together, they ensure that any mission more than 30,000 kilometers from Earth is always in view of at least one station. In 1987, the three main telescopes were expanded further in preparation for Voyager 2's Neptune encounter. When Voyager arrived 2 years later, it revealed at least 4 rings of rock and discovered the Great Dark Spot on the planet's southern hemisphere, a transient hurricane the size of Earth. Winds on Neptune can reach speeds of over 2,000 kilometers per hour. Engineers also altered Voyager 2's trajectory to enable a study of Triton, Neptune's largest moon, which has a thin atmosphere and geysers spraying dark sooty material that drifts across the surface in dark streaks. Neither Uranus nor Neptune has been visited since. Before Voyager 2, they were essentially points of light. What the flyby revealed was that the ice giants are fundamentally different from Jupiter and Saturn, colder, windier, and powered by energy sources that remain only partly understood. We know very little about these two worlds, and many scientists believe it is long overdue to send another probe for a closer look. The Kuiper Belt, Pluto, and the search for Planet 9. Beyond our outermost planets lies a mysterious realm of small, icy bodies, the remnants of the solar system's formation. The Kuiper Belt is a vast region at the edge of the solar system where comets live. Despite its size, it wasn't discovered until 1992. Within it lies a world once called a planet, Pluto, discovered by 24-year-old Clyde Tombaugh in 1930. Following the discovery of several other similarly sized objects in the Kuiper Belt, Pluto was reclassified as a dwarf planet in 2006. That reclassification, however, has not diminished our desire to unlock its secrets. The New Horizons probe was developed to extend Voyager's grand tour to the place those spacecraft couldn't reach. Launched from Cape Canaveral on January 19, 2006, New Horizons embarked on a journey of nearly 5 billion kilometers. At that distance, radio signals take over 4 hours for a round trip. And the probe's download speed was a mere 1 kilobit per second, 50 times slower than the dial-up modems of the 1990s. It took 15 months for all of the data New Horizons gathered to be transmitted back to Earth. Until New Horizons arrived, scientists weren't even certain of Pluto's actual size. The mission confirmed that Pluto is 2,376 kilometers in diameter, the largest of the catalogued dwarf planets. But it was the surface that was truly astounding. A world with nitrogen ice glaciers flowing across valleys beneath mountains 3 kilometers high, made from water ice coated in nitrogen snow. The textures and patterns make it look almost like an artwork in places. Among the most striking features was an extraordinary heart-shaped region of smooth terrain, indicating a surface renewed within perhaps the last million years. As New Horizons departed, it revealed a naturally blue sky created by nitrogen gas, remarkably like Earth's, and the sun illuminating that blue atmosphere against the blackness of deep space. Observations of the outer solar system continue to raise questions. A number of objects beyond Pluto follow unusual orbits that could hint at an unseen gravitational force, a hypothetical world currently dubbed Planet 9. Several outer solar system objects, including asteroids and small icy bodies, appear to be gravitationally nudged in ways that tend not to occur by chance. Their orbits align in one direction, suggesting the influence of a large, distant mass, perhaps between the size of Earth and Neptune. The kind of super-Earth that turns out to be one of the most common planet types found around other stars. Ironically, the most common planetary type in other star systems may be precisely the one missing from our own. If Planet 9 exists, it could be 20 times farther from the Sun than Neptune, making it extraordinarily faint. The most likely region of sky where this hypothetical planet might reside happens to be the densest part of the Milky Way, filled with countless background stars. To identify Planet 9, astronomers would need to detect a dim, slowly moving object against that crowded backdrop. An object that would take between 10,000 and 20,000 years to complete one orbit of the Sun. For now, we are looking for a needle in a haystack where the needle looks very much like hay. Pale blue dot. The Voyagers are now the most distant objects ever forged by human hands, and they have given us our most profound perspective on home. On February 14, 1990, Voyager 1 turned its cameras back toward the inner solar system and captured a panoramic family portrait of the entire solar system. Within one narrow beam of scattered sunlight appeared a tiny, pale blue dot. Earth, seen from the perspective of deep space. That image made everyone stop and wonder about the scale of the universe and our place within it. Both Voyagers have now crossed the heliosphere, the outermost boundary of the Sun's influence, and continue their journey into interstellar space. They carry enough power to send signals back until perhaps the mid-2030s, an astonishing achievement for spacecraft launched in the 1970s. They carry with them a history of humanity as spacefaring explorers and the promise of future discoveries. The Voyager spacecraft fundamentally changed our understanding of what the outer solar system is and revealed new worlds that beckon to be explored. The space race. As the Second World War came to a close, the United States and the Soviet Union rushed to secure Germany's scientific minds and the technology they had developed. Rockets, including the world's first long-range guided ballistic missile, Germany's Vi-2, which could cross the threshold of space, became the prize. American forces secretly evacuated thousands of German scientists and technicians out of Europe in an operation codenamed Paperclip. A Cold War mounted between the two superpowers, and from America's perspective, the Soviets were too technologically backward to develop a rocket capable of delivering a nuclear weapon to the United States. In 1957, that assumption was shattered when the Soviet Union announced the world's first intercontinental ballistic missile capable of carrying a nuclear payload 8,000 kilometers. Although the R-7 rocket proved too large for practical warfare, Soviet leader Nikita Khrushchev permitted his scientists to modify it to carry a satellite instead. Within weeks of the R-7's first successful test, the Soviets ushered in the space age. Bearing the Russian word for traveler, Sputnik climbed over 900 kilometers into orbit. The world had been anticipating an artificial satellite, but everybody assumed it would carry an American flag. A polished aluminum sphere measuring 58 centimeters across, Sputnik transmitted a continuous series of beeps that any person with the right equipment could pick up, proof that the Soviet achievement was not propaganda. All over the world, people tuned in to that characteristic signal. For some, it was inspiring. For others, deeply unsettling. But to hear this artificial thing beeping and sailing overhead put a real panic into some people. And there was a kind of hysteria alongside a fascination that humanity had placed a small object into orbit around the Earth. Thousands of people went outside each night to watch this tiny point of light travel across the sky. It triggered a public interest in space that had not previously been felt at the population level. The space race was no longer a pipe dream. The starting gun had been fired, and America was already behind. In the late 1600s, Isaac Newton had conceptualized orbit by imagining stones thrown horizontally from a mountaintop. The faster the stone is projected, the farther it travels before gravity pulls it to the ground. But because Earth's surface is curved, a stone projected with sufficient speed would find that the ground below is receding at the same rate gravity pulls the stone downward. This traps it in perpetual freefall. That is orbit. The United States Navy attempted to launch America's first satellite just 2 months after Sputnik, but the Vanguard rocket failed on the launch pad. America's space ambitions were then handed to the Army. Wernher von Braun, the V-2 engineer brought over during Operation Paperclip, refined his Jupiter-C rocket to deliver a satellite. Explorer 1 launched successfully, its instruments confirming the presence of a large band of high-energy charged particles, radiation captured by Earth's magnetic field, now known as the Van Allen radiation belts. This discovery directly influenced the design of future human spaceflight missions, which would need to carry crews safely beyond those belts. The first humans in space. In 1958, NASA initiated Project Mercury, its first human spaceflight program. Astronaut candidates were selected from the test pilot ranks of the Navy, Marines, and Air Force, screened not only for physical fitness, but for the psychological resilience required when things go wrong. 7 men were ultimately selected and introduced to the public on April 9, 1959. Following America's announcement, the Soviet Academy of Sciences selected 20 cosmonauts from their Air Force pilots. 6 received accelerated training, and 1 was chosen to be the first human to reach space, Yuri Gagarin. A brilliant mind with the composure and bearing of the ideal Soviet citizen, he was about to become the most famous person in history. On April 12, 1961, Gagarin's Vostok 1 lifted off. Rockets designed to carry humans cannot accelerate as rapidly as unmanned missiles. The G-forces would be fatal, so the spacecraft rose gradually, building speed as it climbed. Within 10 minutes, Yuri Gagarin became the first human to cross the Kármán line, the boundary between Earth's atmosphere and outer space. Looking down, he transmitted back to Mission Control. "I see the Earth. It's so beautiful." The single orbit lasted only 108 minutes. But returning was as perilous as departing. A spacecraft plummeting back through the atmosphere generates extreme heat. The gas at the nose of the re-entry module can reach temperatures hotter than the surface of the sun. In the event, the re-entry capsule failed to separate cleanly from the service module, sending both into a life-threatening spin. Fortunately, friction burned through the connecting cables, and at 2.5 kilometers above the ground, Gagarin ejected and parachuted safely to Earth. Had he remained inside the capsule and landed with it, the impact would have been fatal. Yuri Gagarin's safe return was celebrated worldwide. The path was now open, at least in principle, to explore the solar system. It was an extraordinary act of bravery, and it proved that humans could go into space and not only survive, but perhaps even thrive. A month later, NASA sent its first man to space aboard Freedom 7. Alan Shepard became the first American to achieve insertion into space, though his suborbital flight was not intended to complete a full orbit. The entire flight concluded in under 16 minutes. America's first orbital mission came in 1962, when John Glenn's Friendship 7 successfully traversed the globe 3 times. Unlike Gagarin's flight, which had been shrouded in secrecy, Glenn's mission was broadcast live around the world. Never before had so many people shared an adventure of such magnitude simultaneously across all languages and all media. Over the following years, both the United States and Soviet Union completed 6 solo missions, though the Soviet cosmonauts accumulated far more time in space. The Soviets achieved another historic first in 1963 with the flight of Vostok 6. Valentina Tereshkova became the first woman to travel in space, spending nearly 3 days in orbit, though ground control received reports that she had suffered from space sickness during the mission. The Gemini and Voskhod programs. With a dozen single-occupant missions in the history books, both programs began developing multi-person spacecraft. NASA's Gemini program, approved 3 months before Glenn's orbital flight, took years to design a capsule for two, not a linear problem. The aerodynamics, thermal protection, and life support all became significantly more complex. To maintain their lead, the Soviets retrofitted their one-seat Vostok capsule and placed an extra rocket on the exterior to create the Voskhod. Every gram of weight had to be justified. Crew members even went on diets. The life-saving ejection seat was stripped out, and the crew flew without spacesuits. There were no second chances. If the capsule's pressure was lost, that would have been the end. Voskhod 1 set an altitude record of 336 kilometers, and the crew returned safely. But the mission reflected a troubling trend toward unacceptable risk-taking in the Soviet space program. This was what the space race was ultimately about: achieving something, anything, before the other nation, even if it meant cramming more people into a spacecraft that was never designed for them. While the Americans prepared for their first two-person mission aboard Gemini 3, the Soviets pressed ahead with Voskhod 2, crewed by Pavel Belyayev and Alexei Leonov. The capsule was equipped with an inflatable airlock, enabling Leonov to perform the world's first spacewalk. Once outside, he beheld humanity's first unencumbered view of the planet below, tethered only by a 5-meter cord to a vehicle representing the only barrier between him and certain death. Leonov later wrote that he felt like a seagull with its wings outstretched, soaring high above the earth. But his historic walk quickly turned into a near disaster. His spacesuit began to expand in the vacuum, and he found his hands slipping from his gloves, his boots unable to fit the ends of his suit. He had only minutes to re-enter the Voskhod before the capsule rotated into shadow. In a split-second decision, Leonov vented half his suit's oxygen to reduce its volume and regain mobility, not knowing whether this would save him or kill him. It was the right call. The hatch was finally closed, but explosive bolts that jettisoned the airlock sent the capsule into a spin. Voskhod 2 touched down 2,000 kilometers off course, and the crew spent 2 nights in a Siberian forest before rescue teams found them. There were no further Voskhod missions, a hint that Soviet space supremacy was beginning to wane. Tragedy and triumph. Humanity's foothold in space was not free of tragedy. In January 1967, 3 NASA astronauts perished when fire erupted inside the Apollo 1 capsule during a ground test. 2 months later, cosmonaut Vladimir Komarov became the first person to die in spaceflight when his Soyuz 1 parachutes failed on re-entry. Soviet lunar ambitions were suspended for 18 months. Then, in 1968, Yuri Gagarin, the first human to reach space, died in a jet crash. The following year, America reached the moon. Space stations, from Salyut to Mir. Having conceded the lunar race, the Soviets shifted their focus toward establishing a long-duration human presence in orbit. Beginning in 1971, they launched a series of 7 Salyut space stations, pioneering another first and demonstrating that humans could live and work in space for extended periods. Doing fundamental experiments without the influence of gravity requires exactly the kind of environment a space station provides. In 1973, the United States launched its first space station, Skylab. Essentially repurposing a Saturn V rocket stage, Skylab was the answer to the question of what to do with the Saturn hardware once the Apollo program wound down. The uninhabited station was damaged during launch, a solar panel was torn off and the thermal sunshade compromised, and the first crew had to undertake an emergency repair mission. Despite a challenging start, the station was brought into operational condition. It featured a galley, a zero-gravity shower, and sleeping quarters, and hosted 3 crews for nearly a year. The key experiment was the astronauts themselves. Could humans remain healthy in space over extended periods? The answer, it turned out, was conditional. The heart muscle reduces in size without gravity to work against. Bone density decreases. The shape of the eye can change, and fluids redistribute throughout the body. Astronauts exercised for several hours a day just to maintain physiological function. Human beings, it became clear, are not designed for space. In a moment that became something of a legend, the third and final Skylab crew grew so exhausted that they turned off communications with mission control for a full orbit. The 93 minutes of radio silence sparked negotiations, and the crew was ultimately granted a more lenient schedule, completing all their tasks on time. NASA learned a valuable lesson. Their crews had limits. The Soviet Mir space station, launched in 1986, represented an even more ambitious vision of long-duration habitation. 6 pressurized modules were added to the initial section over time, creating an orbital complex that was assembled piece by piece, the only practical way to construct something of significant size in space. Cosmonauts aboard Mir even straddled the end of the Soviet Union itself. Flight engineer Sergei Krikalev was in orbit when the USSR collapsed, a stateless person circling the Earth and unsure where he belonged. Mir was visited by astronauts and cosmonauts from many nations, including participants from North America, Europe, and the Middle East, as well as a Japanese television reporter, a genuinely international community. By the late 1990s, however, Mir was plagued with malfunctions, mold growth, computer crashes, and even a fire. The station was abandoned in 2001 and left to burn up as its orbit naturally decayed. The Space Shuttle. In the same year humans first stepped on the moon, NASA began planning a reusable spacecraft that would make the concept of going to space more accessible. The Space Shuttle was an aviation system in its own right, generating lift with its wings and fuselage, capable of launching atop rockets and landing on a runway like an aircraft. Space Shuttle Columbia was ready for the program's maiden orbital flight in 1981. Each subsequent launch followed the same routine. 2 solid-fuel rocket boosters flanked the shuttle for the first 2 minutes before detaching to be recovered for reuse. A disposable external tank provided liquid hydrogen and oxygen to the main engines before burning up during re-entry. To endure multiple journeys through the atmosphere, the shuttle was encased in over 24,000 silica fiber tiles. The black tiles on the belly and leading edges could withstand temperatures up to 1,260 degrees Celsius. NASA's fleet of 5 shuttles performed 135 orbital missions over 3 decades, launching satellites and space telescopes, hosting experiments, and delivering modules to the International Space Station. In 1984, astronaut Bruce McCandless became the first human to float freely in orbit, performing an untethered spacewalk using a specialized maneuvering unit, a human being, alone, as their own spacecraft. The shuttle program also endured tragedy. In 1986, Challenger was destroyed 73 seconds after launch when a rubber O-ring seal in one of the solid rocket boosters failed, allowing hot gases to cut through a structural strut holding the external fuel tank. In 2003, Columbia disintegrated during re-entry after a piece of foam insulation shed from the external tank during launch had damaged the heat shield on the orbiter's left wing. 7 crew members died in each disaster. Space is hard, as those in the industry say, and the astronauts paid the ultimate price. But the missions continued after each loss, because that is what human beings do. We learn from tragedy, and we press on. Ultimately, the shuttle program never delivered on its original promise of low-cost, rapid turnaround access to space. The estimated cost of a single launch was once as low as $22 million. The actual average was $450 million. Space Shuttle Atlantis completed the program's final flight in 2011, having fired the imagination of a generation. The International Space Station. As the 20th century drew to a close, construction began on a new chapter in space cooperation. Astronauts aboard the Space Shuttle Endeavour delivered and connected a module called Unity to the Russian module Zarya. The International Space Station was born. It took a decade to fully assemble the ISS. But once the first components were in orbit and the first solar panels were generating power, a crew could live aboard and science could begin. Since November 2000, humanity has maintained a continuous human presence in low Earth orbit. The station opened space to the world in a way never previously accomplished. Following the shuttle's retirement, the Russian Soyuz spacecraft provided the primary means of crew access to the ISS, a testament to how well-designed and reliable that vehicle is. The idea that 50 years after NASA's founding, the United States would need the Russians to transport its astronauts to a space station would have been a mind-boggling statement to anyone in the 1950s. On May 30, 2020, American astronauts launched from American soil once again, this time aboard a SpaceX capsule. The commercialization of space had arrived. SpaceX and the broader wave of commercial space companies changed the economics of spaceflight fundamentally, recovering and reusing launch vehicles in ways that once seemed impossible. The International Space Station serves as the only environment in which humanity can develop the knowledge needed to venture beyond Earth's orbit. It is the test ground for understanding the long-term effects of space on human biology, for learning to grow food in a closed environment, and for developing the self-sufficiency that any deep space mission will require. The story of the ISS will soon come to a close, but its place in history is assured. From seeds of rivalry, humanity opened a gateway to the cosmos. Return to the Moon. Our fascination with the Moon stretches back to time immemorial. Earth's companion was present long before life existed on our planet, and it has always served as a focus of wonder, close enough to inspire, far enough to demand enormous effort to reach. Scientists hypothesize that the Moon formed over 4.5 billion years ago as the product of a collision between the early Earth and a protoplanet called Theia. The impact shed material from Earth's outer layers, which coalesced over time into the Moon. Our natural satellite gradually settled into its current orbit, with one face perpetually turned toward Earth. The lunar dream came into focus following Sputnik's launch in 1957. The Moon became the ultimate prize in the space race, and robotic probes would venture there first. The Soviet Luna 1 was the first object to escape Earth's orbit in 1959, though it missed the Moon by nearly 6,000 kilometers and continued into solar orbit. Luna 2 became the first spacecraft to impact the lunar surface, strewing Soviet medallions across it. Luna 9 achieved the first controlled soft landing in 1966, transmitting photographs from the surface. Though its transmissions were intercepted by the Jodrell Bank Observatory in England, whose operators published the images in a newspaper before the Soviets did. NASA's Surveyor program demonstrated that the lunar soil was robust enough to support a spacecraft's weight, something that had not been certain. While the Lunar Orbiter series photographed 99% of the Moon's surface, identifying the safest candidate landing sites and revealing a world fractally cratered with fresh hazards emerging at every scale of magnification. On September 12, 1962, President Kennedy challenged America to place a man on the Moon before the decade was out, not because it was easy, but because it was hard. The Gemini program served as a bridge, giving astronauts experience with spacewalks, rendezvous, and docking, all essential skills for the lunar voyage. Ed White became the first American to venture outside his spacecraft. Later, Buzz Aldrin performed 3 spacewalks totaling 5.5 hours on Gemini's final mission. To carry 3 humans to the Moon, NASA built the Saturn V, the most complex machine ever attempted. To reach the Moon in a matter of days, the rocket needed enormous energy. As more fuel is added, however, the rocket grows heavier, and gravity holds it back more stubbornly. The Saturn V's development was, at its core, a relentless battle between weight and speed. Apollo 1's tragic cabin fire in January 1967 killed astronauts Gus Grissom, Roger Chaffee, and Ed White. The pure oxygen atmosphere inside the capsule, combined with flammable materials and an inward opening hatch that internal pressure made impossible to open quickly, created conditions for catastrophe. In the aftermath, the capsule was redesigned. Flammable materials were replaced, a quick-release outward opening hatch was installed, and the atmosphere was changed from pure oxygen to an oxygen-nitrogen mixture. Less than 18 months after that tragedy, humans were on their way to the Moon. Apollo 7, the first crewed mission of the Apollo program, demonstrated that astronauts could live and work safely inside the command module, and that the module could re-enter the atmosphere without incident. It was a crucial stepping stone. Apollo 8 remains perhaps the most audacious human spaceflight ever undertaken. Its mission was to circle the far side of the Moon, enter lunar orbit, and return. To be captured by the Moon's gravity, the trajectory had to be perfect. An error of even 1 mile at the moment of insertion could send the crew sailing irretrievably into deep space. When Apollo 8 disappeared behind the Moon, Mission Control had to wait 32 agonizing minutes for reappearance. Not only did Apollo 8 successfully circumnavigate the Moon, but it did so 10 times. The crew became the first human beings to see the Earth rise above the lunar horizon, a fragile blue marble suspended in the vast darkness of space. That image catalyzed the modern environmental movement. It was, for many, a beautiful awakening for all of humanity. Apollo 10 served as a full-dress rehearsal. 2 astronauts descended within kilometers of the surface in the lunar module, practicing every step of the landing approach. Enough fuel was deliberately withheld to ensure no one was tempted to attempt an actual touchdown ahead of schedule. On July 16, 1969, Neil Armstrong, Buzz Aldrin, and Michael Collins launched aboard Apollo 11. While Collins remained in lunar orbit aboard Columbia, the Eagle descended toward the surface. The onboard computer began generating error messages. Worse, it was guiding the lander toward a boulder field. Armstrong took manual control. With fuel dwindling, Mission Control counted down the remaining seconds. 60, 30, The spacecraft touched down with just 16 seconds of fuel remaining. Tranquility Base here. The Eagle has landed. Just 12 years after humanity first breached the heavens with an artificial satellite, we placed our feet upon an extraterrestrial world. Approximately 600 million people watched the broadcast. As Armstrong and Aldrin explored the surface, Collins circled the moon alone, losing contact with all of humanity for 47 minutes on each orbit. It is the most isolated feeling imaginable, and yet, by his own account, also one of profound satisfaction. The astronauts deployed seismometers, collected geological samples, and deployed retroreflectors still used today to measure the precise distance between the Earth and Moon. While the Soviets' Luna 15 attempted to beat them by returning a soil sample to Earth first, it failed. Apollo 11's crew splashed down safely in the Pacific Ocean. Subsequent Apollo missions placed increasing focus on science. Apollo 12 landed near the Surveyor 3 probe, which had been sitting on the Moon for 2.5 years. Pieces returned to Earth showed that lunar dust had abraded Surveyor's camera surfaces, warning engineers that dust would be a persistent problem for surface operations. Apollo 13 suffered an explosion in its oxygen tanks en route to the Moon and had to use the lunar module as a lifeboat for 4 days. The crew improvised a carbon dioxide scrubber from spare parts just to stay alive. They never landed, but they came home. Apollo 14 landed Alan Shepard, the first American in space, on the Fra Mauro Highlands. He smuggled a golf club head onto the mission and, after a disappointing first shot that sliced, struck a second ball that traveled, in his words, miles and miles and miles. Apollo 15 was the first true in-depth science mission, featuring 3 7-hour spacewalks and the debut of the lunar rover, designed and built in just 17 months. With the rover, astronauts could now traverse 12.5 kilometers in a single excursion, collecting geological samples from diverse regions. Apollo 16 challenged existing theories about the lunar highlands, finding that rocks in a region long thought to be volcanic in origin showed no evidence of volcanism whatsoever. Apollo 17 sent a geologist into space for the first time. Harrison Schmitt discovered evidence that the Moon once sustained a magnetic field and returned more scientifically significant material than all the preceding missions combined. On December 14, 1972, as Gene Cernan prepared to ascend from the surface for the last time, he spoke. "We leave as we came, and, God willing, as we shall return, with peace and hope for all mankind." Apollo 17 set several records: the longest human presence on the Moon, the longest extravehicular activity. But with waning political support and budget cuts, future missions were canceled. The scientific legacy, however, was profound. The retroreflectors left on the Moon by Apollo astronauts made GPS possible. By studying the Moon, a world with a common origin with Earth, we learn about our own planet's history. And beyond the science, Apollo demonstrated what was possible when human beings were willing to attempt the truly difficult. A new era of lunar exploration. 14 years after the last Apollo mission, Japan became the third nation to explore the Moon, with the Hypnos probe testing technology for future solar system exploration. Over the following decades, the Moon regained its status as a frontier. The European Space Agency's SMART-1 spacecraft entered lunar orbit in 2004, demonstrating ion propulsion, a novel system that ejects subatomic particles to generate thrust. China's Chang'e 4 delivered the Yutu-2 rover to the far side of the Moon, landing in the South Pole Aitken Basin, one of the largest impact craters in the solar system. Some of the rocks found there have proven surprisingly young, a mystery still being investigated. India's Chandrayaan-1 mission launched in 2008 and confirmed that the Moon, while largely dry, harbors water ice in permanently shadowed craters near the poles. This discovery transformed the calculus of lunar exploration. If water can be extracted and used for drinking, for oxygen, and as fuel, it changes everything about the economics of a sustained human presence on the Moon. NASA's Lunar Reconnaissance Orbiter, in operation since 2009, has collected more data than every other extraterrestrial NASA mission combined. It has mapped the surface with extraordinary precision and identified points of interest for future landers and rovers. NASA's Artemis program, named for the twin sister of Apollo, aims to return humans to the Moon and eventually send humans to Mars. The Orion capsule, designed to launch atop the Space Launch System, represents the spiritual successor to the Apollo Command Module. The program envisions a phased approach. Human landings on the Moon, followed eventually by a crewed Mars mission. Establishing any permanent human presence on the Moon will be exceptionally challenging. There is no atmosphere, no magnetic field to shield inhabitants from radiation, and the wide swings in temperature and constant micrometeorite bombardment create a punishing environment. Water ice at the poles, however, offers a solution. It can be used for drinking, for generating oxygen, and, when split into hydrogen and oxygen, as rocket fuel. The Moon may become not just a destination, but a refueling and resupply station for deeper space exploration. The inner planets. While the outer solar system captured imaginations with its giants and moons, the terrestrial planets closer to home offer their own profound lessons. Each began with a similar evolutionary process, but reached a unique fate, and by understanding them, we learn about our own world. Venus. The brightest planet in Earth's sky, Venus is our immediate neighbor, at a closest possible distance of 38 million kilometers. In the 1600s, Galileo's observations of Venus's phases helped confirm that the planets orbit the Sun rather than Earth. For centuries thereafter, Venus's opaque cloud tops stirred speculation about what lay beneath them, perhaps habitable swamps. In the early 1960s, NASA's Mariner program began developing spacecraft to explore the solar system. After Mariner 1 failed shortly after launch, Mariner 2 became our first interplanetary traveler, conducting the first successful flyby of any planet in 1962. Approaching Venus, however, posed a special challenge. A spacecraft sent toward the inner solar system gains kinetic energy from the Sun's gravity and must be carefully aimed to avoid simply whizzing past at tremendous speed. Mariner 2 revealed a thick, crushing atmosphere almost entirely composed of carbon dioxide. Not the tropical swamps of imagination, but a worst-case scenario, a runaway greenhouse effect. Clouds trap heat, volcanoes contribute carbon dioxide. The heat increases evaporation and produces more clouds, further insulating the planet and raising its temperature. Surface temperatures on Venus reach 475 degrees Celsius, and atmospheric pressure is 91 times that of Earth. Despite being similar in size to our planet, Venus is not our twin, but our cautionary tale. Mariner 2 also confirmed that Venus rotates on its axis in the opposite direction to most planets. A retrograde rotation likely caused by the gravitational influence of the Sun acting on the planet's thick atmosphere over billions of years. The Soviets, meanwhile, targeted Venus for landing. Their Venera program lost early probes to crushing pressure before they reached the surface. But later missions succeeded. Venera 7 made the first transmission from another planet's surface, surviving 23 minutes before succumbing to heat and pressure. While Venera 9 returned the first image from another planet's surface, a black and white photograph of a mundane, rocky terrain. NASA's Magellan spacecraft, launched in 1989, used radar to penetrate Venus's cloud cover and map nearly the entire surface. It revealed a world covered in volcanoes and lava flows, still volcanically and seismically active. Yet Venus's crust is hundreds of millions of years older than Earth's. Unlike our planet, it cannot recycle its rock through tectonic activity. Magellan also suggested that within the first 2 billion years of its history, Venus may have resembled Earth. With liquid oceans and habitable surface temperatures before the Sun's increasing luminosity tipped it into runaway warming. As our own Sun continues to brighten, Earth may one day face a similar fate. Venus is, in this sense, a preview of a possible future, and understanding it may help us understand ourselves. Mercury. Mercury is the smallest planet in the solar system and the closest to the Sun. The solar wind long ago stripped away its atmosphere, leaving it exposed to extreme temperature swings over 400 degrees Celsius during the day, minus 200 degrees Celsius at night. Despite its small size, Mercury is remarkably dense, with a core that constitutes 85% of its total mass, compared to 55% for Earth. Studying Mercury is like peering at the bare skeleton of a planet, stripped of everything but the core, a way to wind the clock back to the earliest days of the solar system. Launched in 1973, Mariner 10 was the first spacecraft to employ the interplanetary gravity slingshot maneuver, flying past Venus and using that planet's gravity to bend its path toward Mercury. It returned over 2,700 pictures across 3 passes, revealing a surface pocked with massive craters, evidence of a period of intense asteroid and comet bombardment early in the solar system's history. The slingshot technique pioneered by Mariner 10 became the cornerstone of virtually every deep space mission that followed. The Messenger spacecraft, after a 7.9 billion kilometer journey spanning 6 years, entered Mercury's orbit in 2011, the first mission to do so. It mapped the planet's polar regions, where craters in permanent shadow may harbor water ice, and confirmed a phenomenon of planetary shrinkage. As Mercury's interior cools, shedding the heat generated during its initial formation, the surface is being pulled inward. The resulting cracks and fault lines scar the planet's surface. Messenger's mission ended in 2015 when, out of fuel, it was deliberately crashed into Mercury's surface, making final measurements of magnetic anomalies and polar ice as it descended. Mercury will not be alone for long. The joint European-Japanese Bepi-Colombo mission, launched in 2018, has been spiraling inward toward the innermost planet, Mars. Mars, a red speck in our night sky, is the outermost terrestrial planet, orbiting at about 1.5 times Earth's distance from the Sun. As telescope technology improved in the 19th century, observers began to record fascinating patterns on its surface. The Italian astronomer Giovanni Schiaparelli described features he called canali, channels, and the mistranslation of that word as canals sparked decades of speculation about a civilization of Martians. In the 1960s, Mariner 4 dispelled those fantasies. Its 21 images showed a desolate landscape of craters and dust, nothing like the Earth-like world some had hoped to find. However, Mariner 9, the first spacecraft to enter orbit around another planet in 1971, unveiled a far more complex world over nearly a year of operation. It revealed a planet of two halves, a nearly flat northern hemisphere and a heavily cratered southern highland. Between them lay a colossal volcanic region, the Tharsis Rise, and a rift valley almost 4,000 kilometers long. Mars possesses the highest mountain in the solar system, Olympus Mons, a giant shield volcano. It has dust storms, weather in its thin atmosphere, and, crucially, fossilized riverbeds and mineral deposits that could only have formed in the presence of standing water. Mars had once been wet. Two Viking landers touched down on Mars in 1976, conducting the first experiments specifically designed to search for life in the Martian soil. The results were ambiguous. The unusual chemistry of the soil, combined with intense ultraviolet radiation, seemed to restrict the formation of living organisms. But Viking's findings did not exclude the possibility that an ancient, wetter Mars once supported life. The Mars Pathfinder mission in 1997 deployed a small rover called Sojourner, demonstrating that a surface vehicle could be operated on another planet, though its range was limited. NASA then developed the Mars exploration rovers, Spirit and Opportunity, twin solar-powered robots designed to hunt for evidence that ancient Mars held water. Spirit landed in a crater that showed signs of having once been filled with water, later covered by lava. After traveling several kilometers to reach nearby hills, it discovered rocks rich in iron and magnesium that could only have formed when the environment was wet and warm. Opportunity landed in a small crater and immediately found layered sedimentary rock, material that forms only in the long-term presence of liquid water. Both rovers vastly exceeded their intended 90-day mission. Spirit operated for over 6 years. Opportunity drove a total of 45 kilometers across the Martian surface over 15 years before a planet-wide dust storm in 2018 cut off its solar power. Its final transmission, decoded from failing instruments, read essentially, "My battery is low and it's getting dark." The Mars Reconnaissance Orbiter, operating since 2006, has circled Mars more than 60,000 times, sending back more data than all other Mars missions combined. Its camera has mapped 99% of the surface in unprecedented detail, revealing a still active and changing planet. NASA's Phoenix lander, operating near the northern polar regions, detected bright white material just 6 centimeters below the surface, water ice. For the first time, we had directly touched the waters of Mars. Among the most tantalizing discoveries has been the detection of methane in the Martian atmosphere. On Earth, methane is overwhelmingly produced by living organisms. It could have a geological explanation on Mars, but it may also represent the first hint of life itself beyond Earth. Future missions will continue to probe that possibility. A human mission to Mars would be a journey of roughly 6 months each way, with a total mission duration of around 2 years. The challenges are as much human as technological. They include prolonged radiation exposure, the psychological demands of isolation, communication delays of up to 24 minutes each way, and the near-complete self-sufficiency any Mars colony would require. But the challenges are not so different in kind from those that previous explorers overcame. Every step taken on the Moon, on the ISS, and in the development of commercial launch vehicles brings Mars closer to reach. The Sun. To comprehend the mechanics of the inner planets, we must understand the engine that drives the entire solar system, the Sun. The Sun produces all the heat and light that enables life on Earth to exist. It also created extreme environments on the other terrestrial planets, stripping Mercury of its atmosphere, evaporating Venus's water, and triggering a runaway greenhouse, and bombarding early Mars with radiation. Its own weather, in the form of solar flares, coronal mass ejections, and the solar wind, influences every orbiting body in the system. When charged particles from the Sun interact with Earth's magnetic field, we see the aurora borealis and aurora australis. But these beautiful light shows come with consequences. Solar storms can disrupt radio communications, damage satellites, and induce harmful electric currents in power grids. To predict that solar weather, we need to understand how it originates. Launched in 2018, NASA's Parker Solar Probe is doing exactly that, approaching within 6.2 million kilometers of the Sun's surface, closer than any previous spacecraft. Two carbon composite plates encasing a foam core shield the spacecraft's instruments from temperatures up to 1,400 degrees Celsius on the sun-facing side. Meanwhile, the instruments themselves operate at a comfortable 30 degrees Celsius. One of the central mysteries the Parker probe is investigating is a long-standing paradox. The Sun's visible surface is approximately 6,000 degrees Celsius, but the corona, the outer atmosphere, reaches 2 million degrees. Temperature normally decreases with distance from a heat source. Why then does the Sun's atmosphere get hotter as it moves away from the surface? There are many competing theories, and the Parker Solar Probe is positioned to test them. Understanding the Sun, the engine of our solar system, is fundamental to understanding everything that orbits it. The future. Mars is the closest destination within human reach, but the challenges are many. A one-way journey would take roughly 6 months, a round trip, including time on the surface, closer to 2 years. The communication delays, the radiation exposure, the need for near-total self-sufficiency, the psychological demands of such isolation, all of these are formidable. Life on Mars would require underground habitats to escape radiation, a breathable atmosphere to be created, water to be extracted from the soil, and food to be grown in situ. It will not be easy. But by solving those problems for the Moon and for Mars, we develop technologies and insights that benefit us back on Earth. Before we set foot beyond our Earth in earnest, however, we must answer a fundamental question. Are these worlds already inhabited? Life may still exist on Mars, perhaps deep underground. Europa, Enceladus, and Titan each present plausible environments for biology as we know it, or as we don't. Until we can say with certainty that a world is sterile, we have a duty to step lightly. To protect potential life out there with the same care we would want applied to our own. Each generation of robotic surveyor has opened new possibilities and revealed that the solar system is more diverse, more dynamic, and more surprising than we imagined. The depths of space called and humanity answered. Our missions to the outer and inner solar system have provided nearly half a century of milestones. Every decade we have learned something entirely new about the system we inhabit. We are, as a species, explorers, from the moment we are born to the moment we die. Without exploration, we do not advance. The question is not whether we will venture to these worlds. It is only a matter of when.